Hello student. In this lecture, we will going to see the simplex lap and wave windings. Okay. So what is a lap winding and wave winding? So this is the types of the DC machine winding. Okay. So in lap winding, there are many parallel paths and number of parallel paths equal to the number of poles. Now what is this parallel path? Okay, so parallel path you will be betterly understand when you see the designs, DC machine designs. Okay, right now I don't have any figure, otherwise I will show that what is a parallel path, but in short you can understand like this, that the parallel path is that which conductors have a same direction of the current. Okay, so if five conductors have a same current of direction, then it will combinedly make one parallel path. Okay, so in lap winding we have a many parallel paths and number of parallel paths is equal to number of poles. So if suppose you have a four poles, then that machine have a four parallel path. Okay, but in case of wave winding, it has a only two parallel paths. Okay, so when the large current are required, so there are we distribute this winding type due to the application. So suppose we have an application in which we require a large current, so in that particular type we will use the lap winding because we have a many parallel paths. Okay, so we can divide this large current into the parallel circuits. Okay, and each parallel paths have to bear a low currents. Okay, so whenever we have a high current machine, in that time in that in that time we will use this lap winding machine. Okay, and another one is that if we have a high voltage machine, then in that case we will use the wave winding. Okay, so both have a different applications. Now how this lap winding is designed. A lap winding is one in which coils overlap each other. Okay, that's why it is named as a lap winding. Okay, so one in which overlap, the coils are overlapping each other. Okay, in this winding the starting and finishing end of the coil is connected to the adjacent commutator segments. Okay, starting and finishing adjacent means nearby, one commutator segment 1 and commutator segment 2. So starting of the coil is connected to the commutator 1, then ending of this coil is connected to the commutator 2. So this is the way where they connected to the commutator. Now what is the condition for simplex lap winding? First is that the back pitch and front pitch must be nearly equal to the pole pitch. Now what is this pitch and all? Simply you can understand that the pitch is a distance. Okay, so we see that the back pitch is a distance between the top and bottom coil sides of the coil. Okay, so and pole pitch is a distance between two adjacent poles. Okay, now YB and YF, second condition is that YB and YF must be odd numbers. Okay, so we have to choose in such a way that they are odd numbers. Okay, they should not be equal, but they should not be equal in case of lap winding, and the difference between them should be nearly equal to the 2. Okay, then YC should be plus or minus 1. Winding pitch Y, which is a difference of YB and YF in case of lap, so it should be a even number. Okay, so now what is the formula for YB and YF? So YB is equal to 2C by P plus or minus K. Okay, so where C is a number of coils, P is a number of poles, and K is a number of making the YB an odd integer. So here we have a condition that YB should be odd number. So if we calculate 2C by P and it gives the even number, then we have to plus or minus the K. Okay, and depending on this K, if 2C by P is a odd number, then we don't have to any addition or subtraction of the K. Okay, and then another one formula is YB is equal to YF plus or minus 2. Okay, so this is come from the second condition, that the difference between the YB and YF should be 2, at least 2. They are not equal. Okay. Okay, so one condition is that the 2C by P must be even in order to make the winding possible. Okay, so this is the condition for the simplex lab. And the next is a wave. So what is a wave winding? Wave, in the wave winding, the finishing end of the first coil is connected to the starting end of the another coil, and which is located under the similar pole. So this is the condition where this finishing end of the first coil. First coil, we have a two coils. Suppose we have a two coils, and finishing end of the first coil connected to the starting end of the another coil. Okay, so in lap winding we have a starting end and finishing end connected to the adjacent commutator segments. Okay, so this is the difference. Now conditions is likely similar, that the YB and YF must be odd number and difference must be 2, but here we have Y which is even, which is a similar condition. YC should be Y by 2. Okay, so this is a different condition from the lap winding, and must be integer. Okay, and formula is also different. Here Y is equal to 2C plus or minus 2 by P by 2. Okay, and YC is equal to Y by 2. Okay, so this is the difference between the lap and wave winding. Okay, now we are going to study the types. Okay, what are the types of DC generators? Okay, so basically mainly we have two types. One is a separately excited DC generator, and second one is a self-excited DC generators. Okay, now what is this separately excited? So in this generator, the field magnet are energized by a separate DC source. Okay, so in these motors, in these type of generators, we use the separate DC source to magnetize the field winding. Okay, so here you can see in the figure that the field winding is connected to the supply through the rheostat. Okay, and armature is just likely connected to the load. Okay, so formula will be Eg is equal to V plus IARA plus brush contact loss, and Ia is equal to IL, same load current is armature current, and power output is a V into Ia. Another one is a self-excited. So in this self-excited generator, further we have three subtypes: shunt, series, and compound. And compound is again divided in two parts: short shunt and long shunt. Okay, so now we will going to see what is this self-excited. So in self-excited, we don't have any external source to excite the field winding. Okay, so simply we connect this field winding in the parallel. If we connect this field winding in the parallel to the armature, then it will become a shunt wound machine. Okay, and if we connect this winding in a series, then it will become a series wound machine. And if we connect this field in a two portion, one is in a shunt and one is in series, then it will become a compound wound. Okay, so here this is a short shunt and this is a long shunt. Okay, so and why this we are making this type of connection? Because each connection have its separate applications. Okay, so now we are going to see what are the mathematical formulas for a shunt, series, and compound. So in this shunt machine, we have a relation between currents like this: armature current Ia. You can clearly see that the armature current is going, and it is divided into ISH and IL. So Ia is equal to IL plus ISH, and Eg is equal to, formula of the voltage is Eg is equal to V plus IARA plus the brush contact drop. Okay, so this is the formula so all in whatever the example in exam or at any stage, if you ask any example of the shunt generator or motor, so there are very minor difference between generator and motor. In generator we have a outgoing current Ia, and in motor we have a incoming current. Okay, Okay, so only there are a sign change, otherwise all the things are same. Okay, so these are the formulas which help you to solve the numericals. Then we have a series wound machine. So in series wound, IA and ISE or IL, all the three currents are same, and if we uh, write the generated EMF equation EG, then EG is equal to V plus IARA plus ISE RSE. Okay, so this is the formula. Then we have a compound. So depending on the type, short and long, we have a different equation. So in short winding, you can see that the here IA is divided in two currents, ISH and ISE. So in this case, ISE and IL are same. Okay, series current and IL, load current, are same. Okay, and in shunt, IA, armature current, and ISE are same. Okay, so now these both motors have a different application. You will see in the further explanation, and these are the equations for that. Okay, so this is the whole structure, that type of DC generator separately and self. We have a shunt, series, and compound. In compound we have a short and long, and in short and long further divided in cumulative and differentially. So cumulative compounded is that the fields in that particular motor are add each other. Okay, so both the fluxes are added together, and in differentially compound it is a subtracted. Okay, now we have a one important concept, that the EMF equation of DC generator, and in many times many exams ask this concept, that how to derive the EMF equation of DC generator. So first of all, note down all the terms. Okay, phi is the flux per pole in Webers, P is the number of poles, Z is the total number of armature conductors, N is the speed in RPM, A is the number of parallel paths in armature, and E is the EMF induced per parallel path. Okay, so now now these are all the terms. Okay, now we are starting the how we can derive, how we can make the equation for the EMF. Okay, so first concept is that in one revolution of the armature, each conductor of it cuts the magnetic flux. So if we rotate the armature in a one revolution, so how much magnetic flux is cut by this conductor is that phi into P. Okay, phi is the flux per pole and total number of poles. If we multiply both the things, then we get the total flux. Okay, now flux cut by one conductor per revolution. Now we are going to calculate the flux cut by one conductor per revolution. So d phi is a phi p. Okay, so this d phi is going to flux per pole and total number of poles, so it will become a phi p. Okay, now another concept is that since the number of revolution made by the armature per minute is n. Okay, so n is a revolution per minute, so it is a RPM. If we want a revolution per second, then we divide this n by 16. So now we have a time, dt is equal to 16 by n. Okay, so time for one revolution is 16 by n. Okay, now according to Faraday's law, we have a d phi by dt. So you will now understand why we calculate the d phi and dt separately. Okay, now put this d phi and dt in the Faraday's law of electromagnetic induction law, d phi by dt. Okay, so if we put both the things, then we get the final formula like this, phi p n by 16 volts. Okay, now another one is that this is for one conductor. Okay, now we want to find the for the all the conductors, all the armature conductors. Then we have a number of parallel paths A. Okay, and number of armature conductor in series per parallel path. So if we have a Z, total number of conductors, then how many conductors are there in a one parallel path? So Z by A. Okay, so if we multiply this number of conductors in series per parallel path, because this EMF is per parallel path. Okay, so if we multiply Z by A with that, so we will get the average EMF induced per parallel path, and this is the final equation. And we will use this equation many times for the numericals. 5 Zn by 16 into P by A. Okay, so this is the formula. And two types of simplex lap and simplex wave. So what is the difference? There is no difference. This is a main equation, but if we further evaluate this equation, then in simplex lap winding, we know that the A is P. Okay, number of parallel path is number of poles. So if we put that, then P and A will get cancel out, and only we left the 5 Zn by 16. And in simplex wave winding, we know that the A is equal to 2. So if we put that, then we have a further evaluated formula. Okay, so this is it for today. In further lecture, we will see the voltage build-up process in the shunt generator. So if you have any question up to now, then you can comment it down. Thank you.